exciting stuff. And now it is my pleasure to introduce our second sponsors of this meeting after Aromics, who are Tunable. Tunable have created a technology that is easy to use, has a very wide spectrum in the infrared, above, I believe, 2 microns, all the way to 10 microns, but Eivind here will tell us the exact numbers, where they can scan that range of wavelengths, where all the interesting organic volatiles and odorants are usually absorbing and emitting. And they can do this scan in real time, and they can tune and teach their system to recognize things without actually doing analysis all the way down to individual molecules. I believe it's a very promising technology. I think we're all here and online looking for technologies such as Aribels, such as tunables, to fit in with our needs, to see where the technology is going. We have an interesting talk later on by Nikhil Lal, who's going to do an overview of the various technologies. And he will address spectroscopy, infrared spectroscopy, also same as Eivind and Tunable are doing. We are thrilled that Tunable has chosen to support us. We have opened our hearts and minds to them, and they have opened their wallets to us and to this wonderful community. So thank you so much, and please tell us all about your sensor and technology. Go ahead.
Can you see my screen?
Yes, we can. And you too. You're good to
go. Thank you so much for the introduction, and thank you all for coming to this presentation. I'm Eivind Ju, and I'm a research scientist here at Tunable, and I'm here to talk about how we use infrared spectroscopy to do machine olfaction, and how this can be a solution to your machine olfaction problems. So, as we all know, the sense of smell is one of the last remaining human senses to be fully digitized, and Tunable have an analyzer based on groundbreaking MEMS technology, making this possible. So this MEMS infrared filter, shown here by our founder, Tolbakke, is the core of our analyzer, and it enables us to detect and identify the fingerprints of nearly all gases and volatile compounds. And I will show you how this can be a game changer when it comes to collecting data and monitoring processes where odors and gases are created. So using our MEMS IR filter, we make this miniaturized infrared spectrometer as shown here and also in the picture. The IR filter enables us to scan the IR for molecules, making it possible to detect almost every gas or volatile compound absorbing infrared light. Furthermore, the analyzer is quite small and has a low power consumption, making it possible to place it practically everywhere, as well as making distributed measurements possible. And then additionally, since our technology is based on optical MEMS, the analyzer is essentially maintenance-free, needing no consumables or service. So now I will show you why infrared spectroscopy is a great technique for machine olfaction. Molecules absorb infrared light at wavelengths that are characteristic to the chemical composition of the molecule. The absorption pattern of each molecule is a little bit different, so we can say that each molecule has a unique infrared fingerprint. And the energy absorbed gives rise to these molecular vibrations, as the one you can see in the bottom of the slide. And in this plot, we can see the absorption spectra for a selection of hydrocarbons. For instance, methane, the red one, absorbs light at wavelength of 3.3 and around 7.5 microns. And many IR analyzers are only able to see a limited window of this infrared spectrum, or several limited windows. And for instance, if this is what you're able to see, then it's really hard to kind of distinguish the different compounds present, right? While we, on the other hand, have this magic flashlight, letting us sweep across the wavelength spectrum and letting us see or smell all the molecules present. And this is essentially what our tunable filter microchip allows us to do. So in the same way as radio stations are spread out in the radio band, molecules have their different locations in the IR. And in the same way as your radio is able to scan the radio band for radio stations, our filter can scan the infrared spectrum for molecule absorptions. So let us look at an example. Ethylene is an important gas arising in many processes, for instance, in ripening fruits and vegetables. And as most other gases, ethylene absorbs infrared light of specific wavelengths. You can see the three dips in this spectrum correspond to absorption of light. And the spectrum to your right is essentially what ethylene would look like for our analyzer. If only ethylene is present, then you might as well just select a single wavelength to monitor it by, and then our scanning capabilities will not be that useful. But however, since there often are other molecules present, such as in this case, methane, you need to see the whole picture to be able to distinguish the two. And often you don't even know which other molecules might be present in your process, making our scanning capability key for separating and distinguishing different compounds in a gas or in an odor. And now I'll show you how we intend to use our analyzer for smelling. I'm starting off with a simplified example, but it's an important one. Controlled ripening fruit, in this case bananas, is of course very important. And in this case, we use our analyzer to smell the crate of bananas. In this case, ethylene is produced during ripening, and if the IR spectrum contains ethylene in some amount, we will see, or the machine learning model trained on the ripening stages of bananas will see this and identify whether the bananas are underripe, overripe, or perfectly ripe, ready for sale. In this case, there is only one gas present, and you might as well just use any other IR sensor. However, since our analyzer can scan the entire IR range, we're not limited to single gases, such in this case. And actually, we're not even limited to knowing what molecules we want to measure. I will show you this. In our labs, we often use this two-component epoxy to your left, which smells quite distinct after mixing. And you can see me mixing glue on the left there. I have no idea what it actually smells or what the smell contains of molecules, but we try to let our analyzer smell it. And our analyzer produces 10 spectrums every second. And to your right, I've selected some spectrums at different times to show you how the IR spectrum evolves during the curing of the epoxy. So after 0 minutes, we don't have any gas from the curing, and we only see, or we see all the light, and we see no absorption features. But after a minute or so, we see a clear feature appearing at 3.3 microns. And then after some more minutes, several more features appear, this time at 3.7, 4.3, and 5 microns. And these features, as you can see, increase in prominence with time. And you can see that after approximately 50 minutes, the transmission spectrum has more or less stabilized, and the glue has actually finished curing. So this epoxy curing experiment illustrates a crucial feature of our technology. By continuously scanning a broad IR range, it is possible and even probable to detect an IR signature in any process where gases and odors are made, even without knowing what it actually is. And additionally, due to its small size and low power consumption, you can put it practically anywhere, as well as making distributed measurements possible. And last but not least, our MEMS technology gives us reproducibility and stability that makes our analyzer easy to use without any need for service or recalibration. You simply install the analyzer and then you get valuable data from your process. So due to these features, our analyzer will be the solution to your problems, ranging from controlled ripening of fruit to monitoring of chemical reactions and processes. So I spent the last minutes describing how our technology can be a game changer when it comes to collecting data and monitoring processes where odors and gases are created. So if you guys have a problem where this is relevant, please reach out to us either by sending me an email or contacting us through our website, tunable.com. And please follow us on LinkedIn. Thank you so much for listening.
Thank you, Tunable and Elvind.
So as we wait for questions from the audience, I have the first question for you guys is this: what do you think? How easy would it be for us to use your machine to do distributed sensing? If we put a bunch of your sensors around, let's say, a biopharmaceutical production process, to learn what the smell of a long series of tubes that are fermenting various things that create drugs at the end smells like, and monitor these changes in real time. Do you think that's something that we can use your machine to learn what the normal chemical process smells like, and then when there are deviations, can we use that signal to maybe stop the process so we can save hundreds of millions of dollars when we're creating a new drug?
Well, of course, I hope so. I guess the key there is to be able to kind of train the analyzer. You have to know what a good process smells like or looks like for our analyzer. You have to tag those good batches, right? To be able to see which or how the spectrum looks when it's a good batch, and then of course when it deviates, then you might have a bad batch, or potentially you can identify if the batch is bad, and then use that as training data for a machine learning model, for instance.
Can we have this?
Yes, of course.
Please point out we can see you from those cameras.
Hi, thank you so much. I'm wondering, is the machine learning model is it analyzing the visual spectrogram data?
Yeah, or so far we're mainly concerned with the hardware, but we think that since our data has a quite high quality in a way, you should be able to use the IR spectrums from our analyzer to label your process. You're using a machine learning models, for instance.
Thank you.
Go ahead.
Yeah, thank you. Since I'm a lawyer, I want to ask you a little bit of a legal question. Maybe not a difficult one, but one question. In I believe your second slide, you had an individual blowing into that whatever. If you go to that, yes. Yep, no. If you can move up, I want to show that. Not this slide.
Or this one? Yeah.
Yep. Yeah. So this individual is blowing into whatever, the little device that you have created, correct?
Mm-hmm.
Right. So now the question I have is, have you done any testing to kind of figure out bad breath?
Not yet. We have.
Not yet.
In this case, we only have measured CO2 and H2O, water, from your breath, not distinct breath of this.
Not distinct. Okay. So that probably answers my second question, is because, we do a lot of breathalyzer tests to determine the alcohol, content that an individual has. Is this a device that can be used in sort of creating a breathalyzer test that is more reliable? Because currently we have breathalyzer tests that are always challenged.
Yeah, sure. I don't know the difficulties with the breath analyzers today, but we can measure alcohol.
Yeah, thank you.
I have one, unless there's other questions, I have one last question for you. Have one? Okay, go after me then. So, Elvind, one more question. I think that perhaps you mentioned this, but I want to drill it into our audience. One remarkable feature of this technology that Tunable has created is the width of their window that they can actually scan. They can chirp the wavelengths. So if you know what your molecule is that you're looking for, then it's easy because you can find the signature from IR spectra, Raman spectra, GCMS spectra, you name it, and then you just try that one molecule in your device, you see what the signature is, you know what it is, that's fine. What about when you don't know what the biomarker or signaling molecule is? Let's say, like Dimitri said, bad breath, Well, bad breath does not have a single molecule that is salient for it. It's not just one thing. There's many things that go into it. If you don't know what the molecules are or where the salience of the signal is, it is fundamentally important to be able to quickly scan the whole range of the signal to find out where the signal is. So I don't know of many other devices that come in a small form factor and are this fast to scan over what is it again? I'm sorry, is it 8 or 10 microns that you can scan over, right?
From approximately 2 to 14.
2 to 14, that's 12 microns range. That is amazing. There's an enormous amount of interesting biochemistry that is happening in this range and reports its happenings and its reactions via emissions and absorptions in that infrared range. Pretty much all of our biology, there it is. Yeah, there you go. So, and a lot of the absorption and emissions that happen in that range of wavelengths have to do with vibrational states of molecules, which are supremely important for everything from olfaction to metabolism, to recognition, to health. So with that, I want to make sure that people realize, talk to Tunable when your problem is to find out what something smells of as opposed to what it's made of, or talk to Tunable if you want to sense an overall signal without knowing where the salience is and you want to find where should I concentrate on. I don't know of a lot of other things that will come at this. Now, I don't know if should put you on the spot, but how much is your device? Is that available? Did you mention it? Can I buy it tomorrow or is it not available yet?
I'm not entirely sure if it's available. I guess you can send me an email and I will answer.
I see. So you don't want to reveal the price point, but okay. I will not drill any further. So Emmett has a question, and then after that, we'll go to our next speaker. Thank you.
Yeah, hi. I'm curious, so if it works when somebody breathes into it, you probably need a very high concentration of the gas in order for it to register on the IR spectrum in a way that's consistent with your model. Is there like a minimum concentration which you require in order for the tech to work, or is there an aspirational point at which you could do it from raw visual data? Like, for example, you take a picture of somebody in the infrared and you can get the right information from that.
If I understand your question correctly, for us, we are basically measuring the amount of light that is absorbed. From molecule to molecule, it depends how much it absorbs of light, and in that case, the concentration you need to be able to see the molecule depends on the molecule. How much?
Well, I guess I'm thinking about exoplanetary spectroscopy right now. How we can detect the atmospheric makeup of exoplanets from 100 light years away, for example, and with this. We're using a very confined environment, but it's the same process. So is there a point at which we could detect these gases without having them in confinement? Just from infrared image data. Thank you.
Yeah, I guess it depends. If you have an IR source, in the case of planets, then that will be the case. You can measure it.
Yeah. Okay, we have one final question from the web.
Yes.
And Carolina will read it for you.
So, Akshan Danish asks, what is the limit of the detection you can achieve, ppb, ppm?
Then again, it depends on the molecule, but in the range of ppbs to ppms, depending on the molecule.
That's great.
Thank you.
So you're getting close to where the dogs and other animals are, which can do PPB or PPT even. So for next is Stephanie and Phil, right? They're ready. So I will, yes?